Log on, tune in, find out. Another good idea from Cambridge.
On Hecke algebras at roots of unity.
Okay, so the purpose of today is to round up things a bit. So I recall, let W be a finite while group. Generating set S. We have defined corresponding generic Hecke algebra with these parameters. So generic Hecke algebra over A, which was this ring of Laurent polynomials. We had the standard basis, these TWs, and we could write down explicitly the multiplication in this basis. And the main point was, whenever we have a ring homomorphism into a field, so we get this specialized algebra. So that's really an honest associative algebra over a field. And one of the major open problems is to understand the irreducible representations of these algebras. The main, or one of the main applications, let me also recall that, was to groups of Lie type. So assume we have such a finite group of Lie type. With while group W and these parameters CS. So we assume these parameters come from such a group of Lie type. Then, if we have K an algebraically closed field of characteristic L, where L is 0, or L is away from the defining characteristic, then we have a specialization from A into this K by sending V to a square root of Q in this field. And then we saw, using this theory of Hom functors, that actually the irreducible representations of our Hecke algebra are in bijection with the irreducible representations of G in this Harish-Chandra series. So this was just this very special case. Let me recall. So this set was defined to be the set of all irreducible representations of G, such that Y is a factor or a submodule of RTG of this Harish-Chandra induction. And I don't remember now if I said this yesterday, but in this special case, what is this Harish-Chandra induction? So it was defined to be, first lift this representation to the parabolic subgroup, which is the Borel subgroup here. So the lift of the trivial representation of T to B is the trivial representation of B, and then you induce to G. So you just get the permutation representation on the cosets of B. So this is just K G mod B. Yeah. And if you like, maybe I should also mention this here, you can even formulate this yet in a different way. Namely, what does it mean that y is a factor module or a submodule of this permutation module? Wait, by Frobenius reciprocity, this simply means that the trivial representation of B is a submodule or a quotient module of the restriction of y to B. Or in other words, it simply means that B has non-trivial fixed points on this module. Yeah? So like this, even if you don't care so much about this theory of Harish-Chandra series, here you have a completely elementary statement that, so you look at all irreducible representations of G such that there are non-zero vectors fixed by all elements of B. So this defines a certain subset of the irreducible representations of G. And by this theory of Hom functors, this is in bijection with the irreducible representations of such a specialized Hecke algebras, where hence the interest of studying this. Right. So now we have seen yesterday that in the case where G is GLN, so W is the symmetric group and all the CS's are 1, then this Hecke algebra has a very nice structure. It's a cellular algebra. And in fact, there was a very strong statement, namely that the Kashtan-Lustig basis is a cellular basis here. So unfortunately, this very nice and smooth statement is not true in general. So it's not true in general. But, so you can still do something, and this is what I want to explain now. How you can still exhibit a cellular structure in Hecke algebras of any finite type. So for this we need some notations. So now the general case, but with one restriction, we let's only consider only G of split type, or in other words, let's keep only this assumption that all these parameters are 1. One can also do something in the unequal parameter case, but it's technically a bit more difficult, and actually it relies on some of Lustig's conjectures on Hecke algebras with unequal parameters. So let me stick to this case here. So we have our H this generic Hecke algebra. We have the Kashtan-Lustig basis in here, and the first thing that we need to do is to define some invariants coming from this basis. For this purpose, we look at the structure constant in this basis. Yeah, so these are difficult to describe combinatorially, but there are some Laurent polynomials. And using these polynomials, Lustig had the idea to define a function. So define a function which is called A, which attaches to each element of W a non-negative integer, and this is done as follows by so fix an element Z in W, then you look at all these structure constants where X and Y run, Yeah, so z is fixed, you let x and y run. So this gives you a collection of Laurent polynomials, and you look at the smallest power of v, such that if you multiply v to the I with this thing, you get real polynomials and not just Laurent polynomials. So we want to find the minimum of all these things. Huh? So this is Lustig's A function. So I could now define or recall a number of properties of this function, but for the purposes of my talk, it will actually be enough just to mention one property of this function, namely given any I, define h greater than or equal to I to be the A span of all Kashtan-Lustig basis elements which have a function greater than or equal to I. So I just take the A span of this inside H, and then it's a deep fact that this is actually a two-sided ideal. Yeah? So is a two-sided ideal. Yeah? So it's a very simple statement, but the proof requires actually exactly this interpretation of the Kashtan-Lustig basis that Pramod mentioned this morning in terms of some perverse sheaves on some Fleck variety and such things. So it's quite a heavy statement here. But you see, actually you obtain a whole filtration of H by these things. So H is this, contains all these, and so on, and it stops somewhere. Actually, one can show that it stops where capital N is the length of the longest element in W. Now, with this chain, we can also, so we can specialize this. So specialize, I will need this. If I specialize the parameter to 1, so from A to C, the specialized algebra is just the group algebra of W. So then this filtration specializes to a filtration of the group algebra of W. Yeah, so we get CW so this is a chain of two-sided ideals. Here. And I need this to introduce another invariant. Namely, now I just look at the irreducible representations of, so I just look at the classical ordinary representations, if you like, over the complex numbers of this finite while group. Once and for all, I choose a labeling set for this. So if you think back of the case of the symmetric group, this lambda would just be the set of partitions of n. And now I choose the name lambda because I want to end up with a cell datum for H. And maybe you remember a cell datum was a certain quadruple. You needed a lambda, an m, and star, and a c. So this will be the lambda in a cell datum for H. But right now I just use this filtration to say the following. So given lambda in lambda, there is a unique I such that E lambda is a composition factor of this piece here. This is a chain of two-sided ideals. So if you like, you could consider even the associated graded algebra then. So you get a direct sum decomposition of CW as a bimodule, which is a direct sum of all these things. And since it's a bimodule decomposition, every irreducible representation belongs to exactly one piece in this partition, and this defines this A. So we define A lambda to be this I. So in this way, get we also get this invariant attached to every irreducible representation of W. Well, I just introduced it like this for the purposes of this talk. There are other characterizations using, if you know about this, generic degrees of the irreducible representations of H and so on, but for the purposes of these talks, it's enough to use this definition. And using this, I can now define a partial order on lambda. Remember, for a cell datum, we need this lambda and a partial order on it. So here I simply define this to be so by decreasing A invariant, if you like. Okay, so with this notation, I can now
Compatible with partial order for Sn?
yes. In Sn, so WSN, where lambda was this, if you have lambda mu in the dominance order, this implies that this A mu.
But not the opposite application.
Sorry?
Not the opposite application.
Not the opposite application. But again, I didn't want to introduce too many notations in my talk. One can actually define a slightly stronger partial order here. If I had introduced two-sided cells, one can attach to each irreducible representation of W a two-sided cell, and then I use the Kastan-Lustig partial order on the set of two-sided cells to transport this to. Yeah, so this is a little bit weaker, but easier to define here. So now I can, well, I need one further piece of notation. So recall, what does it mean to be a bad primes? Well, there's a general definition using in terms of root systems. If you have a root system of some type, an irreducible root system, it has a unique highest root, and you call a prime bad if this prime divides one of the coefficients in the expression of this highest root in terms of simple roots. So there is a general definition of these bad primes for root systems, algebraic groups, and they show up at various places also in the theory of algebraic groups. For example, the classification of unipotent conjugacy classes depends on whether you are in good or in bad characteristic. So it's well known that usually these bad primes cause some trouble, and I will also have to exclude them here. But here I will just use the list of bad primes. So here's a table. So in type A, there is no bad prime. In classical types, 2 is the only bad prime. In type G2, F4, E6, the bad primes are 2 and 3. And in E8, it's 2, 3, 5. Yeah? So this is a known thing. And then I have to make sure that in my whole theory I never specialize to anything with bad primes. So what I will actually do is I replace this ground ring A. So from the beginning we change this definition. I just make the integers a little bit bigger so that bad primes are invertible in this ground ring by A. So where R is a subring in which bad primes are invertible. So I change this notation here. Yeah? And then the theorem is, so and this was proved about last year, that so under the above conditions H is a cellular algebra where, so I have to specify these ingredients for a cell datum. So the lambda is as above, so an indexing set for the irreducible representations of W. Then I need this partial order as above using a function. Then I need these m lambdas. Well, what was it in the symmetric group case? So the capital lambda was the set of all partitions of n. The m lambdas was the set of all standard lambda tableau of shape, of all standard lambda tableau. Well, what should this be in general for type 8 or anything like this? Well, for this you have to simply note that the irreducible representations of the symmetric group, so if you take the irreducible representation labeled by the partition lambda, it has a basis indexed by the standard lambda tableau. So in general, this will simply be a basis of E lambda. Yeah? And this is, cannot expect more here. Then what else do we need? We need the basis elements, the C lambda STs. And this is of course the most difficult to define, and I will not write the precise formula. I will only say that this is a certain specific, well, I could write it down explicitly, but it would require too many technicalities now. Z linear combination of CWs where A of W is A lambda. Yeah? So in the symmetric group case, you could just take Kashdan-Lustig basis elements. In the general case, you have to take certain integral linear combinations, relatively small linear combinations of Kashdan-Lustig basis elements which satisfy this condition. So here you see maybe that this respects somehow this partial order using this A invariant. Okay, I will not say much more about this. This is the general result. So we have this theory, this nice representation theory available that comes from the general theory of cellular algebras. So let me recall the main points here. So recall if theta then is a specialization. So the theory of cellular algebras gave me these modules wk lambda equipped with bilinear forms. An invariant bilinear form. So we can define this L lambda, put an index k here, to be wk lambda modulo the radical of this form. And one of the theorems of Howlett-Lehrer was that then you get a classification of the irreducible representations of this algebra by simply taking those, so I denoted it like this, those of these L lambdas which are non-zero at all. So where this is the set of all lambda in lambda, where this form is not identically zero. Yeah. So as a first application, let's see what happens in the semi-simple case. So this, I should have mentioned this already yesterday in the general theory. So this was also already in the paper by Graham-Lehrer. It does not hold just in the Hecke algebra case, but in general, if you have a cellular algebra over a field, then HK is semi-simple. Well, if and only if all these forms are non-degenerate. G lambda k is non-degenerate for all lambda in lambda. So that means for all lambda the radical is 0. So it would mean that LK lambda is WK lambda for all lambda in lambda. And this is equivalent to saying that these W lambdas are already the irreducible representations of HK. So this somehow solves the case for semi-simple situation. So in particular, in our context, so we see in particular in this case, I mean, if HK is semi-simple, so we see that the irreducible representations are parametrized by lambda, and their dimensions are exactly the same as the dimensions of the E lambda. So this is one way of recovering this Tits deformation theorem that was already mentioned before. So we get here just this bijection. Here the D and note that this has basis given by M lambda, and this has a basis index, so they have the same dimension. This is one way of recovering Tits deformation theorem here in this context. Yeah? Okay, so what happens in the non-semi-simple case? This should be the interesting case now. Yeah, so let's go back to this situation. Yeah, so arising from a group of Lie-type context. So we have this group, we have this field, which we assume now to be of positive characteristic, which does not divide Q, and well, so we can now continue this bijection here. So we know that this set I just recall this bijection there. So this was in bijection with this, and now we know that this is in bijection with this lambda 0 k, a certain subset of lambda. So this proves already one of the things that I had mentioned much earlier in a very rough way, that the irreducible representations of my group of Lie type here, this subset, is not like in the semisimple case in bijection with the irreducible representations of W, but naturally in bijection with a certain subset of the characteristic 0 representations of my Weil group. It's already some statement. Now, how can we further understand this setting? And there I introduce this quantum characteristic again that Sasha introduced yesterday. So L does not divide Q, so I can define this E to be the smallest I such that this thing is 0 in my field of characteristic L. Yeah? So it's exactly the same definition that Sasha used yesterday. And now I guess I'm now heading towards explaining James' conjecture. What can we do now with this E? Well, we can consider, after all, we have this generic object. We can consider another specialization. So let's call it theta E, simply from A into the complex numbers, where my variable goes to an, well, since this is supposed to be the square root of the parameter, so I have to send it to a root of unity of order 2e. And so I get HE, the corresponding specialized algebra. So this is now an algebra over the complex numbers in characteristic 0. So let's just make it explicit once more. It has the basis TW, and the multiplication is given by these formulas, where now the parameter has been specialized. So here is then an eth root of unity. The length goes down. Yeah. So starting with our group and our field K, so we have these two data, the little q, the little l. These two data define this number E, and using this E, I simply define a new algebra over the complex number, which is not in any direct way related to this group. It's not an endomorphism ring of anything there. Yeah? The endomorphism ring interpretation comes when I really work over the same field here. This is just a new thing. But it's a specialization of my cellular algebra, so the same theory of cellular algebras gives me a classification of the irreducible representations here. So you have here, so let's call them, put this index E here. So everything is now over the complex numbers here. Where this set is the set of all lambda in lambda, where this form is not zero. Yeah? And then, of course, we have the natural question, how is this related to the one that we really want to know, this here? Yeah?
Why is it C?
Sorry?
Gename was C.
I mean, well, you are more happy if I put a little e there?
Yeah.
Yeah? Well. Well, I'm specializing now using this specialization. So, I mean, in my older notation, I just put the subscript k everywhere. Okay, so I was not consistent. I should have put a c here everywhere, but yeah?
Not the generic value at all. It's the specialized value.
Yeah, here, of course, yes, yes. So the question is now, relation between this and this. So this here is over C with parameter eth root of unity, and here we are over k, which is characteristic L, and the parameter is well, q mod L. Well, and the best we can say here is this is, so I'm heading now towards James' conjecture, which is one of the big open questions in this field. So this was formulated first by James 1990 for the symmetric group case. But now, since we have this general cellular structure, we can actually formulate a general version of James' conjecture, and this is the following. So we need one further piece of notation. So I consider this Poincaré polynomial. Of W. So this is defined as this polynomial. So it is known that there is a nice product decomposition of this polynomial. So you can write this as a product of rank of W factors, and these di's, these exponents that occur here, are called the reflection degrees of W. So these are the degrees of W, and actually, well, you can also, I have the time, can make a table here, can write them down explicitly for all types. So here you just have 2, 3, 4 to n. Here you have 2, 4, 6, 8, 2n. Here's 2, 4, 6, 2n minus 1, n. Here you have 2, 6, 2, 6, 8, 12, 2, 5, 6, 8, 12, 6, 10, 14, 18, and 2, 8, 12, 14, 18, 20, 24, 30. Well, one of the properties of these numbers is that their product is the order of W. Yeah? You see here in the symmetric group, for example. So now we can state the general version of James' conjecture. So in the above setting, so what do I mean by this? It's still written there. So we have a little q, we have an L, this defines an E. Now we need some conditions. So assume L is not bad. For W, this I erased, so this excludes a relatively small number of primes. And there's a second condition, which is more serious, and that E times L does not divide any degree of W. So this means that L is not too small, where we have a precise condition. And then the statement is simply, that the irreducible representations of this thing and this thing are the same. More precisely, that dim L lambda k is the same as for all lambda in lambda. So in particular, this means they are zero at the same lambdas. So in particular, this set should be equal to this set. So the essence of this thing is that the irreducible representation of such a Hecke algebra in characteristic L do not depend on the individual values of L and Q, but only on this little e here. Or things in characteristic L should be completely controlled by something in characteristic 0. So this viewed as such, it's a quite general phenomenon that positive characteristic is usually considered, or not only considered, but it is actually something very hard. In characteristic 0, you can very often hope to have more machinery available, in particular geometric methods and such things. So you would hope to be able to lift a problem from positive characteristic to characteristic 0. And this is usually a very hard question and very difficult to sort out how small or big your primes have to be so that this works. Yeah?
This in particular is the weaker statement, and there is a chance that it will more often. Can you comment on that?
Yes, I will say this in a second. So in particular, so I just close with some remarks now. So here just as one immediate application, returning to our groups of Lie type. So we see, for example, that this set so I write it once more. So it was written there. It's in bijection with the irreducible representations of the Hecke algebra, in bijection with this lambda 0 k. And if all this is true, it only depends on E here. Yeah? So if under above conditions. Yeah? So this gives already the non-trivial statement that this set here, which highly depends on Q and L and everything, is actually just only depends on this E. Yeah? So some further remarks. So the first is probably, well, it's not too hard to show that such a statement is true as long as the prime is simply large enough. Yeah? So a statement of James' conjecture is true is not so hard to show. Yeah? The real issue is to find exactly from when on it is true. Yeah? So the real issue is to find bound from when on it is true. And this is what this James conjecture does. It gives you a precise condition on L when this will be true. Yeah? And actually I should also say, so James' original formulation for WSN was EL is bigger than N. And well, unfortunately I just erased this table of the degrees. If you see actually that this, in this special case, this translates to this condition here. And there are a number of other heuristic reasons which suggest that this is the right condition in general, that should generalize this condition. Yeah, I don't have time now to explain more about that. But this should be the correct, this thing about this degrees should be the correct generalization of this here. Then second remark is, it's also not so hard to prove, so known, that you always have some inequalities here. So this is always contained in this, and then these dimensions are always smaller than these for all mu in this set. It's not too hard to show. So you see, once you know that this set is always included in this equality can be shown by simply showing that these two sets have the same cardinality. Yeah, so in order to show that this is this, it's enough to show that this is true. And actually this is known to be true. So actually this is known to be true. And it follows by, it can be proved by a general argument under these conditions. So this was done by myself and Rouquier a long time ago actually. 97. So this is a general argument. But if you are willing to also use some case-by-case analysis and everything else that is known for individual types, then this equality holds actually under the single assumption that L is a good prime. Was this your question? Yeah. So this is known to hold whenever L is not a bad prime. But it would be nice to find a general argument for this, but I don't see how to prove this in general. Yeah, then the third remark is probably, so this general theory raises then the question of determining these sets lambda 0e in all cases. Yeah? So, and here again, this is a different story. All this is a general theory, but then you actually want to know what these sets are. Already in the symmetric group case, where lambda was the set of partitions of n, it takes some extra work to determine this lambda 0e. And this was also done already by Dipper James in the 1980s, namely this set is simply the set of irregular partitions of n. So partitions where you don't repeat the same part e times or more. So somehow for other types, then the question is to, if you like, to generalize this notion of irregular partition to other types of groups. So for example, in Bn or Dn, this lambda consists of pairs of partitions of n. Certain pairs of partitions of n. So in Bn you take all pairs of partitions of n. In type Dn there's some extra condition, but in any case you have pairs of partitions to consider, and then you have to find out what should this notion of irregular be. And this is not what one might naively think. You just have to consider individually these two components to be irregular. It's much more complicated. So this was solved by Jacquin using Ariki's theorem and this theory of Fock spaces that was mentioned already in Sasha's talk. And then you have all the exceptional types. Well, there you can do explicit computations. You have a bunch of individual types to consider. Of course, E8 somehow poses the biggest challenge there. But as a result of all that, we can now say that so these lambda are known, and actually James' conjecture is verified here. So this was done by Jürgen Müller and myself, and this was very recent. So you have to use computers in the end, because things simply get very big, too big to do by hand, but you also have to do some theoretical work to reduce it to something where you can simply do computations. And still all these computations, they took, I think, almost a year for the biggest representations in E8, because you have to work out these bilinear forms on the irreducible representations of the Hecke algebra. And for example, in E8, you have some representations which have dimension 7,000 or something like this. So you really want to see this matrix of a bilinear form, so that's a 7,000 times 7,000 matrix whose entries are polynomials. And then you have to specialize first to roots of unity and then into finite fields and see how the rank behaves. So each of these individual computational things is actually quite a challenge there. Yeah? And you have to think on how to compute this bilinear form. Yeah? We saw, I wrote down yesterday an explicit formula for this bilinear form, for the coefficients. It was some structure constants of the cellular basis. But to get the cellular basis, you would have to compute the Kashta-Lustig basis first. So this is, you cannot use this to compute these bilinear forms. But anyway, I don't want to go into too much detail. So the conclusion is we managed to verify that for the exceptional types, these are really the correct conditions there. And if these conditions on this EL does not divide is not satisfied, then it really fails. You will get some strict inequalities there. So it really seems to be the correct bound. So I guess with this I can close, but I just want to say, so this James conjecture is, yeah, in this area of these Hecke algebras, of finite dimensional Hecke algebras, is one of the major open problems. And it would be a great success that when this program in 6 months is over, maybe we know something more about this conjecture. Okay, thank you.
Questions? Well, can we thank Meinhof again and all this morning?